In today's lecture, we are going to discuss the class of circuits called oscillators. These are circuits that, as you know, produce an output, typically a periodic output, a self-sustained periodic output without an input. That's what self-sustained really means. Now, depending on what kind of periodic output is produced, you have different kinds of oscillators. You can have oscillators which produce sinusoidal signals, triangular signals, sawtooth signals, square waves. There are many other possibilities actually. In today's lecture, we will focus primarily on sinusoidal oscillators, oscillators which produce an output which is a nice constant frequency sine wave. Now, every oscillator typically requires these four basic components. At the heart of an oscillator, there has to be an amplifier. There has to be an output limiting device which, as we will explain soon, is required to ensure that the output does not become too big, or rather, in trying to become too big, becomes distorted. There is a frequency determining network, a part of the circuit which decides which particular frequency the oscillator is going to oscillate at, and a positive feedback network. Now, though I have listed these four components, you have to realize that it's not always true that you can break up the oscillator into four modules, each part of which does one of these tasks. That usually does not happen. Very often, for example, the amplifier and the output limiting device are basically the same part of the circuit. Very often, the frequency determining network and the positive feedback network are essentially again rolled into one. Sometimes, as you will even see, it's very difficult to distinguish the amplifier from the positive feedback network. So, these are the four things that the circuit must have for it to be an oscillator. These are by no means sufficient, but these are necessary. However, it may not be true that you can break up an oscillator circuit into these four neat pieces. Always. Sometimes they are just too intertwined to be disentangled like this. Just for the sake of simplicity of discussion, let us at least assume that we have a situation where we can think of the amplifier and the positive feedback network as two separate pieces. And what I'm going to do next is essentially discuss the theory of positive feedback. This is very similar to the theory of negative feedback which we had already discussed before. And the basic idea is something simply like this. We have an amplifier, and we are assuming for the time being that this is a voltage to voltage amplifier, so that the gain is given by AV. In some situations, like if you are using a transistor amplifier, it may be a better idea to think of it as a current in, current out amplifier, something which takes in a small base current, amplifies it to a large collector current or something. However, for the time being, let's stick to a voltage to voltage amplifier picture. So we have an input voltage Vi, and you have this amplifier which has a gain of AV, and the gain, of course, is a function typically of frequency. I've explicitly written that down. If you're wondering why there's a J along with the omega, let me just point out that in almost all situations where there is a frequency dependence, the frequency comes in with a square root of -1 factor, simply because it usually comes in from capacitances or inductances. In either case, the impedance 1 by j omega c or j omega l has omega stuck with a j. So AV, we are going to think of this as a function of j omega. That, of course, would have produced an output VO. What you're doing is you're taking the output, passing it through a feedback network where the feedback fraction beta is again a function of j omega, and this is producing a feedback voltage Vf. This is all very similar to what we did when we talked about negative feedback, although there we may not have stressed the frequency dependence so much. Here the frequency dependence, at least in oscillator theory, is critical. That's why we are focusing on that. The one difference from negative feedback is that Vf and Vi add together and do not subtract from each other. So in a negative feedback scenario, you would have had Vi minus Vf. Here you have Vi plus Vf as a summed input to the oscillator. So what do you have as a result? The output voltage is going to be simply this gain AV which is a function of j omega, times the input Vi plus Vf. So you multiply the input Vi plus Vf to the actual amplifier with AV, you've got the output voltage. And Vf, on the other hand, is simply this beta, which again is a function of frequency, times Vo. Now, if you take this expression, plug it back here, manipulate the equations a bit, it's very easy to see that what you're going to end up with is this expression. Vo is AV j omega by 1 minus beta AV times Vi. So this is again something which is very, very similar to a result we had for negative feedback before. The only difference is there we had a plus sign here. And because of negative feedback, the gain went down. Here, on the other hand, the gain of an amplifier would go up. And that's sort of easily understandable. The output is feeding back and helping the input, so the output should be larger. Now, what we are interested in is the situation where you can have an output, non-zero output Vo, even with a zero input Vi. And it's easy to see that that is possible in this scenario only if this factor in the denominator here actually vanished. And so for self-sustained oscillations, you need to have this criterion. Beta times AV is 1. Of course, this depends on frequency, and because this is usually satisfied only for one frequency, this is how the frequency selection part of the circuit works. Typically, the frequency selection part will work because either AV or beta or both of them depend on the frequency, and so this condition is satisfied only for certain frequencies. Let us just quickly look at what this is telling us about the basic oscillator structure. An amplifier with positive feedback can self-sustain its own oscillations if this criterion, the Birkhausen criterion, is satisfied. Beta A equals 1. What is very important is to realize that beta A equal to 1 is not really one criterion but two, because the left-hand side beta A typically can be a complex number. So what it's telling you is that beta A has to be purely real, at least at this particular frequency at which the oscillations will occur. And at that particular frequency, beta A has to have a value equal to 1. So the feedback has to be exactly in phase. The feedback voltage Vf, which is beta A times Vi, has to be exactly in phase with Vi, which is why beta A has to be purely real. And this loop gain, beta A, has to have a value of 1. However, 1 will not really be enough. To understand this, you have to think about exactly where is the input going to come from. After all, we said an oscillator oscillates without an input. But how does this circuit actually work? If you have an input, A times that goes to the output. A beta fraction of that comes back. So what comes back is beta A times what you put in. And if beta A equals 1, then whatever you put in is coming back, and hence the whole thing can manage to self-sustain, keep on going forever. But the real question is, where is the input going to come from initially? Once you have an input, it's going to self-sustain. If beta A equals 1, that's fine. But where do we get this input from in the first place? And the answer to that is every electrical circuit has a lot of electrical activity going on inside it, even when there is no input signal. And this is because of the fact that electrons inside the components execute random motions. So there's always a lot of electrical noise, which is a tiny random signal of all possible frequencies which are floating around inside the circuit. So basically, it's this electrical noise which is going to provide the input to this circuit so that the oscillations can happen. Now, as I said, typical electrical noise, which is due to thermal reasons, can have all kinds of frequencies in it. Only one of those frequencies will typically satisfy the beta A equal to 1 condition, and so only that part of the noise is going to self-sustain. But that would be tiny. So if it just managed to self-sustain itself, then you will really get a very, very tiny output which will be of no practical use whatsoever. In fact, the output will be smaller than whatever thermal noise the output would usually have, and that's absolutely no good. So what you really need is this. You need to be able to make the tiny input which is coming in from thermal noise grow. So what you really need is not beta A equal to 1. You need beta A bigger than 1 in magnitude for the oscillations to start growing. So then what will happen is a tiny input which is coming in from thermal noise will come back via the amplifier and the feedback loop as a larger version of itself, then that's going to come back as larger than itself, and so on. Now every time the signal goes through the loop, it's going to become bigger and bigger. And that poses another problem. You need it to become bigger and bigger because it's tiny to begin with. So unless you manage to make it grow, you're not going to be able to start any measurable oscillation. On the other hand, if it keeps on growing without bound, you're soon going to hit a limit, because all amplifiers will have a limit to how big the output can be. That could be typically set by the power supply, or in a BJT it could be because the transistor will be driven into either cutoff or saturation. So you will end up with not a sinusoidal input, but a rather strongly distorted one, something which is clipped off at the saturation values. Now if you don't want that to happen, what you need is a situation like this. You need beta A to be bigger than 1 when the output is small. So small output goes through the circuit, becomes slightly bigger, and keeps on increasing. However, once the output becomes large enough, you want beta A to become smaller, so that now beta A can become exactly equal to 1 and the circuit self-sustains at a large, measurable and useful output oscillation voltage. Now to understand what we are asking here, note that in a linear circuit, the output to input ratio, which is the voltage gain, is fixed. So that cannot change as the output becomes bigger. So what we are demanding here is that the circuit must have some kind of nonlinearity thrown in, which will make the output stop growing once it has reached a particular large enough value. So you need an output limiting device, some kind of nonlinearity in your system. Sometimes the nonlinearity is simply what is provided by the circuit components themselves. Remember, no circuit component is exactly linear, especially the transistors or the op-amp, they are not really linear. So you can exploit their own nonlinearities to provide your output limitation. But sometimes it may be useful to throw in extra nonlinearities from outside to ensure that the circuit has an output which limits at a particular amplitude. So we will see examples of this in the particular circuits that we are going to talk about. But this is the basic theory of how an oscillator should work. Now that we have understood how a circuit can be made to oscillate, let us take a look at a particular example. And the first example that we are going to look at is a very, very important circuit. It's called the Wien bridge oscillator. And what we are going to talk about is how we can approach a design of the Wien bridge oscillator. Now this one, the circuit that you see on your screen right now, of course is not a Wien bridge oscillator. It's a standard op-amp circuit. Okay, let me just remind you that by convention, the upper input is always the inverting one. So if I were to mark it, this will be minus, this will be plus. The input is supposed to be given here, the output taken here. This is simply a non-inverting amplifier with gain of 1 plus R2 by R1. This is a standard circuit which you are pretty familiar with. We have already seen this in our discussions on op-amps. This is one part of the Wien bridge oscillator circuit. An amplifier, the gain is 1 plus R2 by R1. This is the second part of the Wien bridge oscillator circuit. It's made out of series RC combination in series with a parallel RC combination. This should be something which is pretty familiar to you from our circuit analysis classes long ago. We talked about this particular circuit there. This was called a lead lag network. And this lead lag behavior of this network is very, very important for the working of this particular oscillator that we are trying to design here. The input to this lead lag network is up here, that's marked Vi, and this is Vo, the output. But let's be very careful. Here, the input to the lead lag network is actually very distinct from the input to the amplifier. Right? The amplifier input is here, and the output of the amplifier is here. The Vi-Vo that we are talking about in this particular part is the Vi-Vo, the input and the output voltages for the lead lag network. Now, the name lead lag network should immediately tell you that the output leads or lags the input. And we can easily figure that out by doing a mathematical calculation, which we are going to do next. But before we do that, let's try to physically understand why this circuit is going to behave like a lead lag network. Remember, the impedance of a capacitor goes down with rising frequency. Right? So at low enough frequencies, 1 by j omega c, the impedance of the capacitor, would actually be much, much bigger in magnitude than the resistance. You can always go to a low enough frequency where that happens. So at low frequencies, what will happen is that in the series RC combination, the combination will actually behave like the capacitor. And the parallel RC combination, the combination will behave like a resistance. Just to remind you, you put two impedances in series and they are grossly mismatched, the series combination essentially looks like the bigger impedance. And if you are talking about parallel combination, the parallel combination looks like the smaller of the two impedances. That's exactly what we are using here. At low frequencies, C has a much higher impedance. So series piece up here behaves like C, and this part behaves like R. So this is like a CR circuit whose output leads the input. When you go to very high frequencies, on the other hand, the capacitor will end up with a very small impedance. So series combination will behave like R, the parallel will behave like C, and you will end up with an output which lags behind the input. Now what is important is somewhere in between, at some intermediate frequency, the output must be exactly in phase with the input, which is what we want. Why do we want that? Remember, we needed for an oscillation this condition that beta A must be equal to 1. That is, the output, the gain of the amplifier times the feedback fraction should be a positive real quantity. In this case, the gain of the amplifier is a positive quantity 1 plus R2 by R1. If you can manage to ensure that there is zero phase shift between the output of the amplifier and the feedback part, then you are going to be able to satisfy at least part of the Birkhausen criterion, that beta A is real. So let's just go to the maths quickly. For the lead lag network, specifically for the lead lag network, remember, not for the amplifier, the output by input ratio is the ZP by ZP plus ZS, where ZP is simply this parallel combination, this is ZP, and the series combination is what we call ZS. So this is simply the series potential division formula at work. VO by VI is simply ZP divided by ZP plus ZS. That of course can be written down as 1 by 1 plus ZS by ZP. And using the formula for the series and parallel for impedances, it's very easy to show that ZS is going to be given by 1 plus j omega CR by j omega C. ZP is going to be given by the Z1 Z2 by Z1 plus Z2 formula, which works out to be R by 1 plus j omega CR. And so this ZS by ZP, this quantity here, is something which you get by dividing the two, which is simply 1 plus j omega CR whole square by j omega CR. And if you open up the square here, you get 1 minus omega square C square R square by j omega CR plus 2. 2 of course from the twice AB term in the numerator. And when you plug all of it back, you get the VO by VI ratio for the lead lag network to be 1 by 3 plus, it was 1 plus Zs by Zp in the denominator, remember? So 3 plus J times this quantity. Basically 3 plus this quantity, which is J times omega Cr minus 1 by omega Cr. Just to point out, when omega is exactly equal to 1 by Cr, this bracket vanishes and Vo by Vi then becomes purely real. No phase shift between the output and the input. That's the zero phase shift between the lead and the lag. And at that particular frequency, the Vo by Vi ratio is real and is exactly equal to 1/3. So what do we do next? All we do is we join the output of the amplifier, which of course is here, this point, to the lead lag network's input, and the output of the lead lag network to the amplifier's input. So basically, we were calling this Vi, but this is really Vo for our oscillator. And this Vo for the lead lag network becomes a Vi for the amplifier part of the oscillator. So the part in yellow that you can see is actually the amplifier part. The part in green is the lead lag network part, or the feedback part. So for this, what we have is beta. We have already calculated 1 by 3 plus J. We had omega RC. We are just identifying RC as 1 over omega 0. And we get omega by omega 0 minus omega 0 by omega. The gain A is 1 plus R2 by R1. So beta A will be real, which is what you want. A, remember, is already real. Beta A has to be real for the Birkhausen criterion to be satisfied. That will happen only if this bracket vanished, and this bracket vanishes only for omega equals omega 0. So the circuit will oscillate only at omega equal to omega 0. And for beta A to be equal to 1, that is for the Birkhausen criterion to be satisfied, we need the gain to be 3, so R2 by R1 must be 2. So the ratio of the two resistances that you choose must be 2. The feedback resistance here must be twice this resistance. However, as we pointed out before, there's a catch there. If R2 by R1 were exactly equal to 2, then this circuit will sustain the oscillations, but those oscillations will be very, very tiny. So what you need to begin with is R2 by R1 should be more than 2. And you want to ensure that once the output becomes big enough, somehow R2 by R1 falls to below 2. Now, when this circuit was first designed, this, by the way, is called the Wien bridge oscillator, basically because if you look at this part of the circuit, the resistors R2, R1 and the lead lag network together, and just redraw it a bit, you should be able to convince yourselves that what you have is the Wien bridge, which we discussed when we talked about AC bridges, again very early on in our course. That's why this is called the Wien bridge oscillator. However, Wien had nothing to do with this particular oscillator. This was designed a lot later. And essentially, this limiting of the output amplitude was a real problem that the original designers faced. In fact, the original circuit was built not using op-amps or BJTs or FETs or things like that, not modern semiconductor devices, but by using valve amplifiers. And the currents and voltages involved were much larger in those oscillators. There, the original circuit essentially involved a situation where R2 was a resistance and R1 was replaced by a bulb, a standard light bulb. Now, why is that a good thing? Because a light bulb has a resistance which depends on how hot the filament gets. Once the output becomes big, a larger amount of current is going to flow through R1, that's going to heat it up more, and you're going to end up with a bulb which is hotter and hence has more resistance. So here you have a situation that the gain could be kept large to begin with small R1, but as the output grows, the gain falls. So this was the original amplitude limiting portion of the circuit. What the original designer did was spent almost his entire PhD work or PhD time measuring the temperature dependence of resistance of various incandescent bulbs, trying to figure out which one of the bulbs will be best suited for a circuit like this. Once he completed his PhD, he teamed up with a partner, opened a small company in a garage, and started making the Wien bridge oscillator. The original designer's name was Hewlett, and his partner was Packard. The two of them together started building this oscillator from Hewlett's basement, and this is how today's huge company, HP, was born. In modern circuit applications, we are usually not going to use this oscillator in a situation where there are such large currents involved that an incandescent bulb can heat up too much. So we need to introduce some other kind of nonlinearity. By the way, if you keep R2 by R1 tuned very close to 2, then it's even possible, especially if you have an old op amp, that the oscillator might be able to self-limit the oscillation just short of saturation so that you can get a sinusoidal oscillation even without any further circuit components. But that would be sort of relying too much on the amplifier not being able to do its job too well. Instead of that, there are many different ways in which nonlinearities can be introduced in a modern op-amp based Wien bridge oscillator. One of them is shown here. To understand how this works, note that all we have done is that we have connected two diodes in parallel. They're opposing each other. You have connected them in parallel, and then you have connected a resistance R3 in series with them, and you have put the whole combination in parallel with R2. So how does this amplitude limitation work? Well, if the output is too tiny, then what is going to happen is a fraction of the output is going to drop across R2, and that fraction would be too small to make the diodes cut in. Remember, in PN junction diode takes around 0.6 volts to cut in, to begin conducting current. So, for very small outputs of this oscillator, the diodes will be cut off. So the R3 will be out of the circuit. So the gain of the amplifier will be given by 1 plus R2 by R1. And if you take R2 to be bigger than twice R1, the gain is more than 3, and the circuit is going to keep on growing the tiny noise induced oscillations into larger and larger values. But once the output becomes large enough, what happens is one of these diodes, depending on whether the output is positive or negative, cuts in. And then R3, which is in series, comes into play and basically comes in parallel to R2, reducing R2, hence reducing the gain. So this is how essentially the diode R resistance combination limits the output in a Wien bridge oscillator. Why do you need two diodes? Because you want to limit both the positive half of the cycle and the negative half of the cycle. If you had used only one diode, then only one half of the cycle would have been limited in amplitude, and you would have had saturation and hence distortion in the other half of the cycle. So this roughly is how a Wien bridge oscillator can be designed. The frequency, of course, is set by the lead lag network. The frequency omega, as we just talked about before, is given by 1 by RC. This, of course, is the angular frequency. The frequency is given by 1 by 2 pi RC. The next kind of oscillator that we are going to look at is called a phase shift oscillator. Just to contrast that with this case, notice that here the amplifier part of the Wien bridge oscillator was a non-inverting amplifier that caused no phase shift whatsoever. And the feedback part actually caused different amounts of phase shifts for different frequencies, and hence here the feedback and the frequency selection network are one and the same. Only one of those frequencies caused zero phase shifts, so the output came back in phase to itself and was able to self-sustain. In a phase shift oscillator, you start with an inverting amplifier, which has a 180 degree phase shift to begin with. And then you try to shift the phase by an extra 180 degrees so that the overall phase shift becomes 360 degrees, which is equivalent to 0. So how do you shift the phase? Well, you can easily make the phase shift by using RC combinations. So that's basically what is being done here in this circuit. So if you look at the part in red, that's just a standard inverting amplifier with gain minus RF by R. So this is again an op-amp based amplifier with inverting and non-inverting terminals marked out clearly, although frankly, as I said, because of the convention, we don't really need to mark them out. But the amplifier has a gain of minus RF by R. It's an inverting amplifier. Then we have a CR part. So there's a 180 degree phase shift, but the CR will try to move the phase back forward again, right? Because R leads, the output of the CR leads whatever is being an input to it. Now you can easily convince yourselves that one CR will simply not be enough, simply because the phase shift which is induced by a single CR is less than 90 degrees. You need to actually overcome the 180 degree phase shift. So even 2 will not be enough, because 2 will produce a net phase shift which is again less than 180 degrees. So you need at least 3 CR networks. And here what we have done is we have taken 3 CRs. You may not be able to see the third right now. Let's see. This is one. This is another. And the third one is this C. And this R. Remember, because of the virtual ground, this point is actually at 0 volts. So this is really C and R to the ground. So you have 3 CR pieces. You have put in unity gain buffers in between them so that each successive CR piece does not load the previous piece. This means whatever fraction VO by VI each one has, you just multiply them together, you have got the overall feedback fraction. So this, of course, makes our life a lot easier as far as calculations are concerned. The feedback fraction, which is what fraction of VO is fed back here, is simply what happens for one CR piece, which is R by R plus 1 by j omega c, times itself 3 times, so raised to the power 3. This simple calculation occurs basically because the unity gain buffers in between ensure that whatever is output here, no current is drawn from that. So this output is unaffected by the fact that there is another CR network and then there's another CR network. So this, of course, can be simply rewritten in this form. You can multiply through by the j omega c and divide, and then this becomes j omega cr by 1 plus j omega cr, and writing RC as 1 by omega c. The omega c stands for critical frequency. This is the form you get. So what you can see is that the phase shift basically which is being produced is 3 times the phase shift produced by this. Here, of course, is there's a j cube in the numerator. So there's a pi by 2. So there's a j in the numerator that produces a pi by 2 phase shift. The denominator has a phase shift tan inverse omega by omega c. So the overall phase shift by this factor is pi by 2 minus tan inverse omega by c, and you raise this to the power 3. So you want this thing, overall thing. For oscillations to occur, you want this overall thing to be 180 degrees. As a result, the original 180 degree phase shift can be cancelled out, and you get an overall 360 degrees, which is, of course, 0. The same as 0. So for oscillations to occur, tan inverse omega by omega c must be equal to pi by 6, because only then will this quantity add up to pi. Of course, that will happen when omega is omega c times tan pi by 6, which is omega c by root 3, 1 by root 3 RC. So the RC phase shift network where you have three RC pieces shifting the phase sufficiently for the thing to come back in phase with the input, has a oscillation frequency of 1 by root 3 RC. However, that's not enough. You have to make sure that the loop gain now is 1 or more. But what does the loop gain turn out to be? Beta here, which now is g tan pi by 6 by 1 plus g tan pi by 6 whole cubed. I just put in omega by omega c is tan pi by 6 here. Simple manipulation, you multiply through by the denominator cos pi by 6, you get j cos pi by 6 by this. This is a pure phase, as you can obviously see. Cube it out, you end up with a very, very simple result. This beta is minus 1/8. Remember, our gain was minus RF by R. So this R, remember, is working both as the input impedance to this amplifier, also the R in the CR, simply because of the virtual ground here. So you can actually cut down on a circuit component that way. And once you've done that, you have beta was minus 1/8, gain A was minus RF by R. So for beta A to exceed 1, which is when you will have oscillations beginning, RF must be bigger than 8 times R. If you keep it very close to 8 times R, the op-amp's own nonlinearities may be enough to give you sinusoidal oscillations. Typically, you would have to use other output limiting parts like those diode combinations that we had for the Wien bridge. But that's sort of similar to this. But you have to notice that all we did was we had a 180-degree phase shift because of the inverting amplifier. We put in enough RC pieces to shift the phase back to 360. Well, we could have dispensed with the unity gain buffers in between and just use CR. And here, just for the sake of simplicity, I have chosen this R as a separate thing from this R1, and we are going to assume, again for ease of design, that R1 is much bigger than R, which means that in this CR combination, almost entire current is going to go through R and very little is going to go through R1. Remember, R1 is connected back to this. And that essentially ensures that you can think of this as 3 identical CR pieces just connected like this. Now the calculation for beta for this, which is VF by VO, is a standard straightforward calculation using standard AC circuit methods. Just series parallel calculations. However, it's a bit lengthy and I'm not going to work it out for you. I'm just going to tell you what the answer is. The beta, which is VF by VO, turns out to have an expression like this. I would urge you to try calculating this yourself. The unity gain buffers that we had introduced in the previous circuit had the advantage of isolating input from output for each RC stage. So you could just take the transfer function for one RC network and just cube it to get the final answer. Here it has to be calculated with more care. However, the final result is pretty easy to interpret. Notice that A is purely real. It's negative, but it's purely real. And here you have minus j from the j cube in the denominator. So you have a j in the numerator apart from the minus sign, which of course combined with the a would give you a plus sign. So what you need is that the denominator should also be purely imaginary so that the j's cancel. So the real part of the denominator, which has come from here and here, should cancel each other out. That means omega by omega c whole square times 6 must be exactly equal to 1. For oscillations to occur, the frequency has to be equal to omega c by root 6, 1 by root 6 RC. So this is a different value from the previous circuit simply because of the extra loading which each RC stage puts on each other. With the same resistance, same capacitance, you are getting two different oscillation frequencies in the two cases. Not only that, the value of beta at at this frequency is also different. You can easily check that beta turns out to be minus 1/29th here as opposed to minus 1/8 in the previous case. So here what we want is the gain of the circuit of the amplifier must be at least minus 29 in order that the oscillations start growing. So R2 by R1 has to be bigger than 29. So this is the condition for this particular oscillator to work. Once again, you need amplitude limitation components to put in, or you need to adjust your feedback gain to tune it to almost equal to 1 and so on. So before we leave the topic of phase shift oscillators, let's look at a slightly different version. We have been talking of op-amp based oscillator so far. Just for variety, I'm throwing in a PJT based phase shift oscillator. This part, the part in red that you can see, is a standard CE amplifier circuit that we had discussed earlier. And here, these capacitors are blocking capacitors, and we are not using a blocking capacitor on this side. We are just using the standard CRC, and we are feeding it back through an R prime back here. Now, if you just were to analyze this circuit for high frequency behavior, the DC part of the biasing, etc., can be calculated as always. The blocking capacitors here and here, which will act like a blocking capacitor in DC, will essentially detach the feedback part completely from the circuit. The CE will be open at low frequencies, so the standard biasing calculations will work. And then R1, R2 will come in parallel for the AC analysis as we had done before. RE will be shorted out, RC will come joined to the ground. Again, things we had already discussed before when we were talking about the CE amplifier. And what we can do is we can take the small signal approximate H parameter model, and we will end up with basically this. So this is the RC. There's an HFE IB. Of course, there's an HIE which comes in along with it, but that HIE is joined to this point, which is here. And if you choose R prime in such a way that R prime plus HIE is exactly equal to R, you again get 3 CR pieces. Remember, you need at least 3. With 2, the phase shift is not enough. Now, this is of course different from what we have been seeing so far, basically because so far we have been discussing voltage to voltage amplifiers, but here is basically the current IB, which is the current here, that gets amplified to HFE IB on this side. So it's really a current to current scenario. However, the idea is pretty straightforward. If you calculate this IF by IB using this circuit, forgetting that this current is IB for the time being, you end up with this expression. This again is a rather complicated looking expression, but ultimately all that is there to it is basically simple circuit analysis, AC circuit analysis. If you work this out, this is what is going to come out. Now, of course, for this circuit to be able to self-sustain, it has to be consistent with IF being the same as the current IB. So whatever current is here, that essentially is amplified here, and that amplified version produces this current, which is itself. So you need IF by IB. This is really beta A for this circuit. That has to be equal to 1. And if you insist on this being equal to 1, the two parts to that, the purely imaginary parts must cancel. From that you will get this expression. And once you plug that back in, you end up with the IF by IB ratio, which should be actually more than 1 to begin with. But if you set it exactly equal to 1, this is the HFE you get. In fact, you actually need an HFE which is larger than this. Of course, you might ask, is it possible to get an HFE larger than this? Because notice, this depends on R and RC, of course. But there comes the question, if I use an R and RC, where the ratio is too big, I might end up with a huge value for HFE required for oscillations. On the other hand, if you look at this expression, it should be easy for you to figure out that this expression on the right hand side has a minimum as you change R. So that will give you the minimum possible value of HFE for which oscillations will be self-sustained. Any smaller HFE for your transistor, this circuit will not oscillate, no matter how you change your R or RC. So basically what you would do is try to figure out whether that is a feasibility, that is, whether the R by RC can be chosen in such a way that the minimum value for HFE is obtained, and if you have an HFE bigger than that, it's going to work. Frankly, you will find that the HFE minimum which comes out from this expression is somewhere of the order of 50, and most transistors have a bigger HFE than that. So you don't even have to keep R by RC at the value which keeps the right hand side at its minimum. Even a larger value would do. Once again, amplitude limiting networks and other issues have to be addressed. The final kind of oscillator that we are going to discuss are called tuned oscillators. These are oscillators where the frequency essentially is set by things called tank circuits, LC combinations, which essentially can oscillate only at a particular frequency. Tuned oscillators are actually very good for high frequency work. Now, here I have shown you a schematic of a tuned oscillator where you have an amplifier, the part in black here, which has some gain A0 and an output impedance ZO. And what you have are three impedances connected like this, Z3 in parallel to this Z2, Z1 series combination, and the whole thing is fed back. This voltage is fed back to the input. We are going to assume, just for simplicity of analysis, that Zi is very, very large. So this amplifier has a huge input impedance, so draws almost no current from this combination. So you can think of Z2 and Z1 really as a series. But the output impedance ZO is going to be critical for the analysis, as you will soon see. So what is the actual gain of the circuit? The actual gain of the circuit is not AO, because remember, the output from the output side, the amplifier essentially looks like AO times VI in series with the ZO, and you have this whole combination, which I'm calling ZL for the time being, connected here. ZL is this Z3 parallel with Z1 plus Z2. So A is going to be AO times ZL by ZL plus ZO. So that's the actual gain, right? Because the output voltage, whatever you get here, is actually AOVI times ZL by ZL plus ZO. So this is the actual gain of the amplifier. What is the feedback fraction? Well, what fraction of the output voltage is being fed back? For that, the advantage is we have assumed that this amplifier here has a very, very huge input impedance, draws almost no current. So feedback fraction beta is going to be simply Z1 by Z1 plus Z2, just the series potential division formula applied at this stage. So A beta is simply this factor which you get when you multiply these two and simplify things a bit. Now, let us just assume for simplicity that the three impedances that I connect to make up my frequency determining network or tuned network are all pure reactances, that is either inductances or capacitances. So Z1, Z2, Z3 are all purely imaginary. They are JX1, JX2, JX3 respectively. And if you substitute that, what you see is that this becomes minus X1, X3. This becomes minus X3 into X1 plus X2. Of course, the minus sign can be cancelled between the numerator and the denominator. And this becomes minus j omega ZO, where ZO is the output impedance of the amplifier, which I am assuming is real, is purely resistive, times X1 plus X2 plus X3. So under this situation, for oscillations to occur, what must you have? You must have X1 plus X2 plus X3 equals 0. So the point is, these reactive components must be mixed. You can't have three inductances or three capacitances. You must have a mix of inductances and capacitances for the tuned amplifier circuits to work. And at the frequency at which this will occur, X1 plus X2 plus X3 are all frequency dependent. So typically this condition will be satisfied only at a particular frequency. And at that frequency, this one drops out. And X1 plus X2 is of course minus X3 then. So if you put everything together, A beta comes to be minus A0 X1 by X3. And so if you want A beta to be equal to 1, it's not enough just to think about the phase, you have to also think about the sign. If the amplifier is inverting, then minus A0 is positive. So for A beta to be positive, you need x1 by x3 to be a positive number, which means both x1 and x3 must refer to the same kind of reactance. That is, they must both be inductances or both be capacitances. So in that case, x2, the third one, must be of the opposite kind. On the other hand, if A0 is non-inverting, that is, if the amplifier itself is non-inverting, A0 is positive, you already have a minus sign here. So x1 by x3 must be negative, in which case you need two opposite kind of reactances. Either x1 or x3 must be an inductance. One of them must be an inductance, the other one must be a capacitance. So this is how a tuned circuit can be designed. Now, depending on whether you use two capacitances, one inductances, how do you connect them together, whether you are using an inverting amplifier or non-inverting amplifier, you get different kinds of tuned oscillators. Some of the important kinds are called Pierce oscillators, or Colpitts oscillators, or Hartley oscillators. We will look at a few of them later.